Oh, cool. Graphing derivative functions today. Oh, this is exciting. Yep. Now, one of the things that you do need to, this is how I think about it when I'm doing sketching of the derivative functions, is if you've given a function and then you have to sketch the derivative function, it's going to be 1 degree less than the function that you're given. Yep. So what I mean here, just dialing it back, if you are given a quadratic function and you need to sketch the derivative function, you have to know that if you're doing a quadratic, it's degree 2. Its derivative function is going to be a degree less than that, so it's going to be a degree 1, which is a linear function. Yep. So straight away you know what type of function it's going to look like. Likewise, if you've got a cubic here, you know when you go to sketch that, its derivative, it's going to be 1 degree less than 3, which would be degree 2, which is a quadratic. Yep. So that's the first thing you need to be, I think about in my mind. Yep. Next thing that's important is the turning point or the stationary points of inflection that exist on the original functions. What happens is where there is a turning point in the derivative function, that becomes significant. It becomes the x-intercept. Yep, where it crosses over the x-axis. Yep. So what I would do if I was sketching this, for example, and I had to consider drawing the derivative function on the sheet, you know that at this value a, it's going to cross over that x-axis. So I'd put that on there. Next, I would look at the gradient or the slope to the left of this a value here. Yep. So hopefully you can see the slope here is it's going down, it's negative. So to the left of a in our derivative function, it's going to be in the negative section, so below the x-axis here. And you can see from here to here, it's all below the x-axis. It's in the negative section because the gradient was negative here. Likewise, to the right of a, you can see the slope is going back up, it's positive. So to the right in the derivative function, it's going to be in the positive section. It's above 0, okay, on the x-axis. And that's really what this is talking about here. Likewise, if you've got the cubic, same difference. We've got a local maximum here, and we've got a local minimum here. They're important. So on the derivative function of these, or the derivative graph of these, at point A, it's going to cross the x-axis. So I'd go down here and I'd mark on A. Yep. Likewise, we know something's going to happen on the derivative function at this particular point C. So we mark on the point C. Next, we go and we say, okay, to the left of this part, point A, what's the slope? Okay, it's going up here in a positive direction. So in the derivative function, to the left of A, it should be in the positive section of the graph. And you can see here, from here, this way, it's all above the x-axis. Yep, it's in the positive section. To the right of point A here, and to point C, so between this interval A and C here, the gradient is going down. It's negative gradient. So the slope's negative. So on the derivative function, I would expect this section to all be below 0 on the x-axis. You can see here, between A and C, it's all below the x-axis. Likewise, from here to the right of point C, it's got a positive gradient. So from here, it's above the x-axis. Yeah. So that's the way you really need to think about these things when you go about sketching them. Yep. Worked examples are pretty self-explanatory. It's just saying sketch the graph of the derivative function for each of these. So again, if you've got a linear equation, the derivative of that's just going to be a straight horizontal line of the gradient of that line. So okay, you need to think about what the slope is of this. Okay, Here it's obviously going across 1 up 1, so the gradient's 1. You can see here we're sketching the derivative function. Yep. Likewise here, it's got a run of 2. Run of 2 and a rise of -2. Rise over run is -1. You can see here the derivative function. Again, we've got a cubic, so you know in your mind, okay, the derivative function is going to be a quadratic. The points where it's going to cross over the x-axis are going to be -1 and at +1. So I'd go down and I'd mark those on the graph. So to the left of -1, it's got a positive slope, so it's going to be above the x-axis at that particular point. You can see here, where they've marked those on, it's above at that point. In between -1 and 1, it's a negative gradient, so it's going to be below the x-axis at that point. Which you can see, it's below the x-axis. To the right of this, as we said, it's got a positive gradient here, so it's going to be in the positive section above the x-axis here. Yep. This one here is a cubic. Yep. You know that there is a point of inflection here, stationary point of inflection. So at that stationary point of inflection, which is happening at 0, you know it's going to cross the axes of the derivative function. Touch the axis, sorry. From here, you know that to the left of this particular point, the slope was positive, so it's going to be above the axis. As you can see here, this one to the right, it's in a positive direction, it's also going to be above. This one's similar, except here's the spot it's a stationary point of inflection. You can see how that affects it over here. Actually, sorry, the stationary point of inflection is, yeah, here. Yep. This one here is a quadratic. Something's happening here at 2. Now that's the y value. The x value is 0, so it's 0, 2. Okay. So at 0 is where it's at the minimum. So that's where it's going to something happening on the x-axis. Yep. To the left of this, it's got a negative gradient, so it's going to be below. To the right, it's in a positive gradient. It's going to be going above the x-axis here. Alrighty, it says for some functions of f there are values of x for which the derivative f dash x is not defined. It says we'll consider differentiability informally here and more formally in section 9m. So don't panic about this too much. We'll have a chat later on down the track. But really what you do need to know is if you had, for example, a hybrid function, obviously you can work out what the gradient is at each of these points here. And you can work out what the gradient is here. But right at this particular point, where they join, it's not possible because it's too sharp. It's too much of a point there to actually work out the gradient. Is it, is it going down or is it going up, or what's going on? Like you can't. It's basically not being able to be done at this particular point because it's sharp. And this will go through the information of how they've come to that. So essentially, what happens is you work out what the gradient is, obviously, for this part of the hybrid function. You work out what the derivative is at this right-hand side of the hybrid function. But at this particular point here, it cannot be done. And so what we do, we represent that with a little open circle, showing that it's not differentiable at that particular point. And also, when you're writing out, it actually has that notation. So it's not greater than and equal to at that particular point because it's got the open circle. So it's just greater than and it's less than. So here It says draw a sketch of the graph f dash where the graph of f is as illustrated. Indicate where f dash is not defined, so where the derivative is not defined. So again, you should be able to see that there's a very sharp point at x equals 0. It's not, you can't differentiate at that particular point because it's too sharp. So what we do, we can show the derivative function up until this point, and we've got the open circle because it's not differentiable at that point, and then we can draw the derivative function of this part here with the open circle at the start, so forth here.